Hi everyone, welcome to my channel. In continuation to our previous discussions on matrix vector multiplication and how it can be interpreted as linear transformation, we have created 2-3 videos to understand the concept in detail. Here we are talking about matrix multiplication and how we can see its geometrical interpretation in terms of linear transformation. So the agenda of this video is we would be talking about how we can compute matrix multiplication, means how we can multiply two matrices. So first we will look at some pattern to understand how we can compute matrix multiplication, because it's always easy if we visualize the pattern rather than remembering a formula. Second, we will be also talking about the formula which will help us to compute matrix multiplication, but it is not really required because mostly for larger matrices we use software and tools for computational part, right? So we will be looking at the pattern and we will be just writing a formula for a 2x2 matrix, and after that we will try to relate it to linear transformation. We will look at the geometrical interpretation of that. And finally, we will be talking about some properties of matrix multiplication. So let's start first by looking at the pattern, how we compute matrix multiplication. Many of you might be already knowing the same, but let me just explain it with simple example where we have two matrices and both are 2x2 matrices. We will look at another examples of different dimensions also, but as of now I'm taking the matrices of 2x2. So let me take small numbers so that it becomes easy to compute. Suppose these are two matrices which we want to multiply. Now how we compute the matrix multiplication, I'll show you two different patterns here and you will be able to understand the computation as well as you will be able to relate it to what you have learned in the previous tutorial if you are observing it nicely. So first pattern which I usually do when I compute matrix multiplication manually is I take the first row of the first matrix and I take the first column of this matrix and I do multiplication. Multiplication means I will multiply element wise and I will add up those things. So let me write the result here. Here the first element would be, first element means first row and first column. This element will come from first row of this matrix and first column of this matrix. So it would be 1 multiplied by -1. This is the element wise multiplication, plus sign, and this 2 multiplied by this 0. So this is 2 multiplied by 0. If you are doing it for the first time, you might find it little confusing, but after practicing it for a few more matrices, you will find the pattern to be a very nice idea to compute matrix multiplication. So this would be the first element of the resulting matrix. Now what comes here in this first row and second column would be first row again. We would be taking second column now and we would be writing the result here in first row, second column. So let's multiply. 1 multiplied by 2. This is 1 multiplied by 2 plus this is 2 multiplied by 4. So 2 multiplied by 4. Now we have second row and these two columns. So we will repeat the same pattern to compute the things. Let me just show you. This time I am working with the second row. Again I am working with first column first of all. So this is again 0 multiplied by -1. I am writing these things, but we kind of do these computations mentally once we get comfortable. Now -1 multiplied by 0. Similarly, we multiply this here. So 0 multiplied by 2 and -1 multiplied by 4. So the resulting matrix would be, this is -1. This is 2 plus 8, 10. This is 0 and this is -4. So this is the result. So you have seen the pattern. What we are doing, we are taking the row of the first matrix, column of the second matrix, and we are multiplying like this, element wise multiplication and adding those elements. One more thing, if you have noticed that result is also a 2x2 matrix. We will talk about the dimension of resulting matrix in a short while, but as of now we are understanding that multiplying two 2x2 matrices, we are getting 2x2 matrix here, right? Now let me show you another pattern before we move ahead to relate it to linear transformation, what we have learned earlier. So we will do the same matrix multiplication, this time by using a different pattern. So my matrices are 1, 2, 0, -1. The next matrix was -1, 2, 0, 4. The same example we are doing, right? Now, if you remember from our previous discussions that a matrix represents a linear transformation, and if we write a matrix like this, basically it represents that the first column represents that where I hat lands after applying that linear transformation, and second column represents where j hat lands after applying the linear transformation, right? If we are using the standard basis, which we use most of the time, right? So basically this first column represents the coordinates corresponding to x-axis and second column represent the coordinates corresponding to y-axis, and same for this matrix as well. So this time what we are doing is we are trying to find out a new matrix, and here we want to see where I hat lands after applying this matrix and after applying this matrix, right? And where j hat lands after applying these two matrices. So we want to see where I hat lands after these two transformations and where j hat lands after applying these two transformations. In what order, why we are talking about these things, if you are finding these things confusing, just have patience and first look at the computation, then we will talk about geometrical interpretation as well. So first of all, we want to see where I hat lands. If I just apply this matrix, suppose this is matrix A and this is matrix B. Suppose I just apply this matrix B on some vector. So this is the coordinate of where I hat will land after applying this matrix B, right? So we want to see this is the position of the new vector. And this new vector, if I again apply one more transformation to that by this matrix A, where it will land. So what I want to see basically is multiplication of this matrix, which is my first matrix here, on the first column of this matrix. And this should give me the coordinate where I hat lands. Right? So let me try to do this computation. I hope you remember this is simply matrix vector multiplication, which we have seen earlier too. So matrix vector multiplication, either you can do by the same pattern which we have just done, or you can multiply it like -1 times 1 0 plus 0, this 0 times next column, which is 2 minus 1. Sorry for the bad handwriting. So basically it becomes first element is -1 plus 0 and second element is 0 plus 0. This is -1 0. So this is the coordinate where I hat lands, right? So let me fill it here, -1 0. Now we want to do the same computation for second column. So let me do it on the next slide. Second column multiplied by this matrix 1, 2, 0 and -1. So this would be 1, 2, 0, -1 multiplied by, what was the second column there? This 2 and 4. So this is again matrix vector multiplication, and as we have learned in the previous tutorials, how we can do that is 2 multiplied by 1 0 plus 4 multiplied by 2 minus 1. So this would be 2 plus 8 and this would be 0 minus 4, or you can say 10 minus 4. So this is the vector where j hat will land if we apply two matrices in this particular order. So let me fill this column in the previous slide. This is 10 minus 4 here. So if we are using this pattern of matrix multiplication, then too we are getting the same matrix which we were getting earlier. Let me check from the previous slide. -1, 10, 0 and -4. This is yes here. -1, 10, 0 and -4. Same matrix, right? So although this pattern looks having simpler steps to compute the matrix multiplication, but I wanted to show you this pattern also because this is giving us an idea about how matrix multiplication can be understood as a combination of different linear transformation. Now I would say again, if you are not sure what is a linear transformation, how it is related to matrix vector computation, then go back and watch the videos before you move ahead to this. So what you have noticed is we are multiplying these two matrices A, B, and What does it mean geometrically is that suppose you have a vector u. In this vector, you multiply it by a matrix B. So BU, it is basically representing a certain linear transformation which is converting this vector to some another vector V, right? Now you are again multiplying it with the matrix A from the left hand side. We will talk about order again. So this time you are multiplying it with the matrix A. So basically this would be matrix A, same as applying the matrix A on vector V. And we all know that this is again some linear transformation which will result in some other vector W. So basically if we are multiplying two matrices, it would be same as applying two linear transformation in a particular order. In what order? Basically we take the order from right to left. Like first we apply this linear transformation, then we apply this transformation. So in this particular order, if you apply two linear transformation, it would be interpreted as the matrix which is the result of matrix multiplication of these two matrices, right? If you are still not sure what I am talking about, you can relate it to functions definitions. If you have learnt about functions, you might have seen that. Suppose you are working on some input x and you define a function f of x which is nothing but x plus 5. You are adding something to this input, right? Suppose you define another function on the same input g which square the value of x, right? So this is x square. Now if you want to apply these two functions one over another, this is called composition of functions in algebra. You might have read about these topics earlier. So how we denote it is FOG, which is composition of function on the input x. What does it mean is you first apply the function g on x, and whatever is the result, you apply function f on that input, right? So basically here also you work from right to left when you talk about composition of function. Same concept we are generalizing for matrices, right? So what would be the result in this particular example? This would be f of what is gx? It is x square, right? And if you apply function f on this input, so what does this function do? It just add a quantity to this. So this would be x square plus 5. So basically you are starting with input x and you are landing at this output by applying two functions in a particular order, and we call it composition of function. So same concept, same logic we are applying to matrices as well. So we have two matrices here. Suppose A is some matrix, B is some matrix. And in this example, we have just taken 2 by 2 matrices. We will talk about dimensions of matrices. But as of now, let's understand it with 2 by 2 matrices. Then what I'm trying to say is, if we want to multiply these two matrices, it would be same as applying a linear transformation corresponding to this matrix B on some vector, and then applying the linear transformation corresponding to this matrix A on that particular vector, right? So basically it is again in the same order right to left. Now I did not find any suitable web applet which can help you to visualize this particular thing, but what you can do is you can either search on you can search for some applet which shows you this in interactive manner, or otherwise as an exercise, or if you are not yet satisfied how this can be a composition of transformation, you can take some linear transformation. In the previous tutorial we have talked about rotation and shear, these kind of transformation and the corresponding matrices. So you can take some of the known transformation which you know and which you can visualize where this transformation goes and what are the corresponding matrices. So you can apply these two transformation one after another in that particular applet, or you can do the mathematical computation and you can verify whether these two things are same or not, right? So we have talked about matrix multiplication and how it is related to composition of linear transformation. If you want to write the generic formula for matrix multiplication, so for 2 by 2 matrices, it would be simple. For example, AB, CD, and another one is again a 2 by 2 matrix. So this is suppose EF, GH. I am writing ABCD, EF, GH so that you find it little easy to understand. Usually in mathematics we don't write it like this. We write A11, A12 like this, and here we can take B11, B12, B21 and B22. So basically we should use the standard notation which can be generalized for m and n dimensions as well. But for those who get confused by looking at these subscripts and generalizing it to m cross n dimensions, they can understand it with simpler formula. And anyways, we are not going to compute matrix multiplication manually. We have tools to do that. Probably I'll show you how to do all these things using Python or R. So let me just write the formula. We have seen the pattern. If you remember what we were doing, we take this row and we take this column, and we put here in first row, first column. So for first row and first column element, we should get first row of this matrix and first column of this. So this would be AE plus BG. Now to get this element right here, this is in my first row and second column. So this is first row, second column. Let's multiply. So it will be AF plus BH. And similarly, if I need the elements for the second row, I need to do with the second row. So this is CE plus DG, and now this with this column. So this is CF plus DH. So this formula I have written for 2 by 2 matrices. I don't want to scare you by writing a formula for generic matrices. But let me show you one important point to note, which you should always remember, that whenever we do multiply two matrices, their dimensions should be in a particular manner. For example, if this is a M cross N matrix, then this matrix should have n rows, whatever number of columns, but it should have n rows. So I'm just writing n cross k. So basically I want to say that to be able to multiply two matrices, the touching dimension should be same. Means number of columns in the first matrix should be equal to number of rows in the second matrix. Let me just write touching dimension should be same, or we can say number of columns in first matrix, or we can matrix on the left hand side should be equal to number of rows in the second matrix, which is in the right hand side, right? Why this condition should be met? For example, if you are multiplying these matrices A, B, C, D, and here you have two columns in this matrix, and suppose here you have E, F, G, H, I, J, three rows, then how the multiplication would be possible? You would be multiplying A with E, B with G, but there is no other column to be able to multiply it with this I. That is why if we have three columns here, then we need to have three rows here. So for compatibility, we need to make sure that we have the touching dimensions to be the same, right? So this was the condition. Now let's talk about some properties of matrix multiplication, which you should remember is that matrix multiplication is not commutative. It means if you do A multiplied by B, it is not equal to B multiplied by A. Now proof I'm not doing, because you can take any two matrices and you can prove. In general, if you multiply matrix A with B, it is not equal to matrix B with A. The order matters here, right? It is contrary to multiplication for numbers. 3 into 2 is equal to 2 into 3. But because here we are multiplying using a certain pattern, the numbers would not match if you do it in the reverse order. And same you can understand it is if you apply a particular linear transformation, then you apply another linear transformation, the result would be something else if you do it in the reverse order. So that is one property to notice. Second property is that it is associative in nature. Those who are from math, they are already familiar with these terms: associativity, distributivity, commutativity, and all those things. Associative property means if you are multiplying three matrices in this order or in this order, both are same. Basically, the position of parenthesis is changing. So what does it mean is if we are multiplying it in this order, it means first of all we are working with the matrix C and multiplying it with the matrix B. So BC is the resulting matrix which we are getting. Now whatever we are getting, then we are applying matrix A on the result, right? So we are doing this A multiplied by the product BC, right? So this will give us left hand side. And in right hand side, what we are happening is, first of all we are starting with matrix B and we are multiplying it with matrix A. So we get A, and in this AB matrix we are again applying it from the right hand side to matrix C. Means this should be on left, this should be on right, because order matters. Remember, order matters, right? And these two things are same. So this property holds good for matrix multiplication, but the proof becomes tedious if you take 3 generalized matrices. Even if you start with 2 by 2 matrix and you do these matrix multiplication, it will take some time to prove the result. But if you want to see the geometrical interpretation, it would become quite obvious to understand why this property holds good. Because you see, when I am doing this particular thing, what I am doing is, on a vector U, I am applying a matrix C. So this is a matrix vector multiplication. It means this is a linear transformation. So I am applying this particular linear transformation. Now whatever result I am getting, I am applying another transformation AB on that. And now AB, the transformation corresponding to AB, I can break it into two parts. The transformation corresponding to matrix B and then the transformation corresponding to matrix A. So what we are doing is, ultimately on this vector U, we are applying 3 transformation in this order. That first of all, transformation corresponding to matrix C, then transformation corresponding to matrix B, and then transformation corresponding to matrix C. And we are looking at what is the resulting transformation, right? And if we work for the left hand side, again we are doing the 3 transformation in the same order. So we can prove there intuitively that these two things are same, right, without doing the computation. So if you want, you can play around by taking some coordinates, rotating the axis, or doing some transformation and verify the result. If you want, you can take some matrices and get your hands dirty on matrix multiplication and prove these properties. In the next video, we will talk about inverse matrix. Thank you for watching.